This week, engineers woke up to AWS bills in the billions of dollars. A hobby project running a single tiny database, $15 a month, suddenly showed a balance of $87 billion. Cost Explorer agreed. The cost and usage report agreed. Budgets started firing alarms, and for a few hours, a lot of people genuinely thought they were bankrupt. They weren't. Nobody was charged. But what broke is one of the most instructive system design stories of the year, because the bug isn't exotic. It's a mistake any of us could ship. So let's treat this like a real post-mortem, the way a staff engineer would in an interview. What was the system? What was the single point of failure? Why did it fan out so far? And what would you have built differently? That last question is the one that gets you hired. First, model the system, because you can't reason about a failure you can't draw. Cloud billing is not one service, it's a pipeline. At the bottom, metering. Every service emits usage events, instance hours, gigabytes stored, requests served. That's the raw truth, and it's enormous, trillions of events. Those events get aggregated per account, per service, per usage type. Then, the step that matters here, a rating or pricing stage multiplies each unit of usage by a unit price to produce a cost. Finally, that's presented in three places you know: the billing console, Cost Explorer, and the cost and usage report. And it feeds budgets and cost alerts. Here's the crucial architectural fact. The numbers you see in those three products are estimates, computed continuously through the day. They are a separate path from the actual invoice, which is finalized on a slower, more carefully validated cycle. Remember that split. It's the hero of this story. AWS's own root cause statement is precise and worth reading, like an interviewer would. An issue with unit pricing within the estimated billing computation subsystem. Unpack that. The bug wasn't in metering. Usage was measured correctly. The bug was in the rating stage, the unit price. If the price of, say, a gigabyte hour is corrupted, off by a factor of 1 billion, then the arithmetic is still correct. Real usage times a broken price equals an absurd cost. That's why a real, tiny, correctly measured database produced a real-looking, catastrophically wrong bill. This is a subtle and important interview point. The system didn't crash. Nothing threw an exception. Every component did exactly its job. The failure was semantic. A bad input propagated cleanly through healthy code. Those are the hardest failures to catch, because your health checks are all green, while your output is nonsense. Now, the design lesson that matters most. Why did the billing console, Cost Explorer, and the cost and usage report all break together? Because they are not three independent systems. They're three views over one shared computation. The rating output is computed once, upstream, and all three consume it. So a defect upstream doesn't cause three separate bugs. It causes one bug that appears in three places simultaneously. This is blast radius, and it's the thing senior engineers obsess over. When you centralize a computation for consistency, which is a good instinct, you want all three products to agree. You also centralize failure. Consistency and blast radius are in direct tension. The interview-grade insight. Shared dependencies are invisible on an architecture diagram that only shows the three products. You have to draw the thing they all point to. The single points of failure are almost never the boxes. They're the arrows that quietly converge. So how do you catch a semantic failure where all the code is healthy? You bound your derived data. A bill of $87 billion for a single account is not just wrong, it's impossible. An impossibility is something you can encode. This is the layer that was missing, or too weak. Sanity checks on outputs. Concretely, 3 cheap defenses. 1. Absolute bounds. No single account's daily estimate should exceed some ceiling without a human in the loop. A hobby account jumping to billions should hard stop, not render. 2. Rate of change and anomaly detection. If an account's cost jumps 1,000 times, day over day, quarantine that number and flag it rather than publishing it. 3. Unit price validation at the source. Prices live in a narrow, known range. A price outside it should fail a contract test before it's ever used in a multiply. The theme connecting all 3, validate at the boundary and treat derived numbers with the same suspicion as user input. The reason this is hard in practice: at AWS's scale, impossible values are rare and legitimate huge bills exist, so the bounds have to be per-account adaptive, not global constants. That nuance is exactly what separates a senior answer from a staff one. Here's the part that saved everyone, and it's a deliberate design choice, not luck. The displayed numbers were estimates. The actual invoice, the thing that charges your card, runs on a separate pipeline with stronger validation and a slower cadence. AWS's own message said it plainly. The displayed estimates do not reflect actual usage and charges. This is a pattern worth stealing. Separate the fast, approximate user-facing view from the slow, authoritative, money-moving system of record. The fast path optimizes for freshness. You want to see today's spend now. The slow path optimizes for correctness. It's allowed to take hours and double-check, because being wrong there has real consequences. When the fast path broke, the blast radius was contained to information, not money. Compare this to a design where the estimate and the charge share one path. The same bug would have produced $87 billion credit card charges. The separation turned a financial catastrophe into an embarrassing dashboard bug. That is the entire value of source of truth isolation. Watch how AWS actually recovered, because it's textbook and it's a checklist you should be able to recite. Step 1. Stop the bleeding. They paused the estimated billing computation entirely. That's a hard call. Pausing means the dashboard goes stale, but stale is far better than confidently wrong. Step 2. Revert to the last known good state. They rolled back to the last accurate estimated data, meaning customers would temporarily see numbers only through a couple of days prior, but correct numbers. Step 3. Recompute forward once the pricing fix is in. 2 capabilities made that possible, and they're what you should design in from day 1. First, the system could be paused independently. Computation was decoupled from presentation, so freezing the compute didn't take the console down. Second, they had a last known good snapshot to revert to, which only exists if you retain versioned prior states rather than mutating in place. Rollback isn't a button you find in an emergency, it's an architecture you commit to early. If your system can't answer what was the last correct state and can I return to it, you don't have a recovery plan, you have hope. One more, because it's on us, as the users of these systems. Budgets fired alarms off the corrupted estimates, thousands of false pages. If you build alerting on top of an upstream data source, your alert is only as trustworthy as that source. A good budget alert has its own sanity layer. Alert if spend crosses the threshold and the value is within a plausible range. Otherwise, a bad upstream number becomes a 3 a.m. page for nothing. So, what would a staff engineer take from this incident? Draw the shared dependencies, not just the boxes. Bound your derived data like it's untrusted input. Separate the fast estimate from the authoritative source of truth. And make rollback a design commitment, not a fire drill. None of these are exotic. They're the fundamentals, and this week they were worth billions of imaginary dollars. If you want to reason about systems like this, blast radius, guardrails, failure modes, and defend your choices out loud the way an interviewer will push you, that's exactly what Crackit is built for. Practice a real system design interview, free at crackit.io. Draw the system, then go defend it. See you in the next one.